and Christiane will talk about optimally controlled quantum discrimination and estimation once we see her screen. I don't see anything yet.
Yeah, I'm still trying to share it.
And maybe let me take this opportunity and also thank Christiane for organization of all schools, but also of the whole QuSCo event in general, so that we can actually listen to all these very interesting talks. So with this, thanks, and we're looking forward to your talk.
Thank you very much, Stefan. And it's a pleasure to give you some updates about our current activities in optimal control for quantum sensing. And let me start by emphasizing a point that you probably all are aware of, but a point that nevertheless sometimes is not fully appreciated. So what do we mean when we say quantum control? We mean the control of quantum systems, and that means we have resources at our hand, namely interference, or the fact that quantum objects are matter waves and are subject to the superposition principle, and entanglement. So for interference, it means that because you have the superposition principle, you have relative phases, and you can use this and tune the relative phases as an agent of control. And similarly for entanglement. And then we have control knobs that are our external fields that can be either also quantum, as we have just heard in the talk by Patrice, or that can also be classical. And the main point is that the kind of control that we are doing here in QuSCo is that we consider both quantum and classical fields, but we typically do not account for the measurements. So we are really focused on what is called open loop quantum control. And this type of quantum control is very closely tied together with the field of quantum technologies, because also quantum technologies seek to exploit the quantum properties of nature, the main two quantum features, namely the coherence of matter waves and entanglement, and try to exploit these for technological applications such as computing, cryptography, and so on. And what we're focusing on in this network and in this conference is quantum sensing. And you probably also all know that decoherence is typically our enemy, because it destroys the useful quantum properties that we want to utilize for quantum technologies. So when we speak about quantum control for quantum technologies, we really are considering the control of open quantum systems. And that is an interesting field in and by itself. So even if you're a theoretician who doesn't care too much about the technological aspects, this field has something in for you, because there are really a lot of fundamental questions which are still open once we consider a quantum system that interacts with its environment and at the same time is subject to external control fields. And these open questions are: what are viable quantum control strategies? We only know a handful, really. How do these depend on the properties of the environment and or the coupling? And what are fundamental limits to quantum control once we consider open quantum systems? And while, as I said, most of the time we think of decoherence as our enemy, we should also keep in mind that sometimes there is a dissipation-enabled control, such as cooling or qubit reset. I just mentioned it here. It's not something I will focus on today. So our tool, and I mean now within the QuSCo network, our favorite tool for this is quantum optimal control. And quantum optimal control starts from defining the objective in terms of a goal functional, where we say we have an initial state that evolves under the action of some external control to a final time uppercase T, and then we want to match it with our desired target state. And the machinery of quantum control relies on treating this goal or this objective as a functional of some external field. And then one way to obtain the external field is to use variational calculus. Of course, we should also include additional constraints that will allow us to talk to our experimental colleagues. And then just use the rules of variational calculus and get a set of coupled equations that we have to solve, and that will tell us how to choose this external field. So that's a machinery that is fairly well known to the audience. Now let me make the hour a little bit smaller and refer now to what my own group prefers as a major tool for quantum control, and that is Krotov's method, as Eran already mentioned yesterday. And Krotov's method is peculiar in the sense that the quantum version of it, so when you apply it to quantum system, works actually better and more straightforward than the original version developed by Krotov for classical mechanics. And the reason for that lies in the compact nature of quantum state space.
Christiane?
Yes.
May I interrupt you for a second? Can you move slightly the microphone away from your mouth, because there is a bit of breathing noise.
Okay, is it better like this?
Speak again, because now it's a bit soft.
It's too soft, so this is better? Is this better?
Yes.
Okay.
Better.
Thanks, Mattia. Okay, so let's come back to Krotov's method, and the reason why in my group we like it so much is that it's really a very flexible approach that allows you to include nonlinear equations of motion that you have in case of an effective description of quantum systems. It allows you to include dissipation, nonlinear coupling to the controls, and also non-convex target functionals. And let me give you a very first example that Andrea alluded to already yesterday in a slightly different context, and that is we can use now this machinery for the fast and accurate preparation of circular Rydberg states. So we can move in the Rydberg manifold that you've already seen yesterday. And the circular states are the states at the two ends of the diamond here that are particularly protected from decoherence. So preparing them means you're protecting your quantum system. And their name is circular because the orbit of the wave function looks like is indicated here with the nucleus in the middle. And let me just really highlight the main points of this joint work, which has been going on for some time between my group and the group at Collège de France, headed by Michel Brune and Sébastien Glaise. So some of you may have seen some of this before. This is the setup for the experiment with the Rydberg atoms. And what I'll show you in a minute is how quantum control allows us to do the state preparation more accurate and faster than before. And one of the main lessons that we learned in this collaboration is in order for quantum optimal control theory to be successful in collaboration with experiment, you better make sure that your model captures what's going on in the experiment very well. And one way to check is to apply something that both in experiment and theory is known very well, such as a pi pulse, that moves you from this m=1 state here to the circular state. And this pi pulse, you see, if you would stop it at something like 95 or so nanoseconds, would give you something like 80% fidelity, and the timescale is of the order of 100 nanoseconds. Now, 80% is not bad, but the question is whether you can do better. So this was the control problem that we tackled, and you see that we can bring up the fidelity close to 100% in theory, of course, very close to 100% in experiment. You have some remaining uncertainties, in particular for the measurement of the state. And the control protocol that you need, that is shown up here, is not so difficult. You have a modulation of your controls and then still a flat amplitude like in a pi pulse. That allows you to prepare a spin coherent state and then rotate the spin coherent state. So we can do the same state preparation that I showed you before for a pi pulse, but much more accurate. That's nice, but what is more exciting is that you can also prepare states for which you do not have a protocol that is known from analytical calculations, for example, like a pi pulse. So here's another example where we prepared a non-classical superposition state of the circular state shown in black here and the m=1 state shown in orange. And we can do this with the same fidelity, about 96–97%. And the control shapes are still comparatively simple with some modulations and then a linear increase and decrease in amplitude. So quantum optimal control, if you have a model of your system dynamics that is reliable, really allows you to go wherever you want, even in a large and complex Hilbert space. But from a theoretical point of view, what I've shown you so far is a bit cheating. Because I told you we really have to care about the control of open quantum systems. And the control strategy that I exploited so far was just to beat decoherence by operating really fast. So now let's go and think, how can we use the same machinery for open systems? And let's first inspect our target functional that was written here with Hilbert space cats. And coherent evolution. So how do we have to change this slide that I showed you before to account for open quantum system dynamics? And let's pause for a moment and say, well, what this means is really you have to think about how you encode the physics that you want in your optimization functional. And remember that this encoding involves two steps, because you have on one hand your final time target that defines what you want at the final time uppercase t. And you also have this intermediate time contributions that can be time-dependent costs or also state-dependent costs. And both of them are functionals of the external field. Now, if our system undergoes an open system evolution, we have to describe it by a density matrix. The time evolution is given in terms of a dynamical map, which can be obtained, for example, by solving a Lindblad master equation, but could also be something more complicated, including memory effects. Now, if you want to go from a given initial state to some final state, then it seems on first glance to be very straightforward to generalize your target from Hilbert space cats to density matrices and say, well, instead of optimizing the scalar product between my propagated state and my target state, I now do the equivalent for density matrices, namely optimize the Hilbert-Schmidt product. There's a pitfall, though, and I'll come to that in just a minute. And I just want to mention before going there that you can also generalize the gate optimization where you have a desired unitary and an actual unitary. You can generalize this to Liouville space. In the brute force way, this would be done again via the Hilbert-Schmidt product. And now you have here a potentially very large sum. And what we showed a couple of years back is that actually you don't need to do this with a very large sum that is the dimension of your Liouville space, but rather a much smaller number of states is sufficient. And you can minimize a functional that contains 3 very specifically chosen states and get the same. Okay, but now let's come back to the problem that you may encounter if you're using for the optimization a Hilbert-Schmidt product, as is shown here for the real part or the absolute modulus square of your Hilbert-Schmidt product. Because this may actually fail sometimes, and it fails whenever your target state itself is not a pure state but is a mixed state. And it's very simple to understand this with the example of a qubit that undergoes a single decay channel, and we can control this decay. So let's look at a qubit prepared in the, let's say, spin-up state, and this is our decay channel. So this relaxes to this mixed state, and this may not actually be, if you now optimize to reach this target state with a given purity, then what your control will do is it will overshoot and not reach that. So you really are not getting what you want. So a functional based on the Hilbert-Schmidt product may not be reliable. And you may wonder whether maybe this is not really a meaningful target, but I will come to targets where the mixed state assumption is actually meaningful. But before that, let's see what happens, and then let's see how we can remedy this. So for any finite dimensional Hilbert space, we can expand the state in a traceless basis and then get a Bloch sphere representation. And for a mixed state, the Bloch sphere of the target state is, of course, smaller than that of a pure state. Now, let's assume you have a first state that has radius 1 and differs from the target by some angle theta. And then you have another state that takes the same angle with our target but has a larger radius. Then you'll see that what matters is what you would want to matter is the projection onto the target state. But what happens if you take the Hilbert-Schmidt product is that you always will maximize towards the state that has maximum radius, and that's not what you want if you're targeting the green state here. So let's make this more quantitative and mathematical. What do we need for an optimization functional to be reliable? Well, first of all, we want the functional to take a real value so that we can measure whether it's better or worse. Then we want it to be symmetric in the states. And the third condition, which is the one that's violated in the example I just showed you, is that it takes its minimum if and if only the two states are identical. And if we want to use our optimization functional in a gradient-based method, such as a Grape or Kotov's method, then we also want this distance measure to be derivable so that we can take analytical derivatives. Now, in quantum information, there exists quite a large number of distance measures, and I listed here a few. So the trace distance you may be familiar with, or the Bürst distance, which is particularly important in quantum sensing, or the Hellinger distance, the Shannon distance, and the Hilbert-Schmidt distance, which differs from the Hilbert-Schmidt product, because here you really take the difference between two states. Now, if we check these three criteria for reliability, we will find that all of these measures are actually reliable, but only one of them is derivable, so can be used easily in numerical gradient-based optimal control, and that's the Hilbert-Schmidt distance. So let's use this. And if we write this in our Bloch sphere representation, then this is how it looks like. And our geometrical picture on the Bloch sphere actually suggests that maybe we can use this, but we may also want to optimize separately for the angle part in our geometrical picture on the Bloch sphere and the radius part. So we want our target state to match both in angle and in radius. And we can express this easily in the Bloch vector picture, and we can also translate this back into the actual state vectors given by the density operators as this. Now, let's use this these two functionals in an example where you really do have a mixed target state, and that is a squeezing in optomechanics. Let me remind you very briefly what are squeezed states. If you have two non-commuting observables, the most common ones or most well-known ones are, of course, position and momentum, but it may also be amplitude and phase, and there exist many other examples. Then, if the variance of the two non-commuting observables is identical and takes the minimum value for this product, then you are in a coherent state. And of course, you always have to obey this Heisenberg uncertainty, but you can also do this with one of the variances being smaller and the other one larger, and that's exactly what is a squeezed state. And already Patrice in the previous talk mentioned that this is a very interesting resource for quantum sensing because it corresponds to having sub-shot noise correlations. Skip this and jump right to our application, and that is what's called quantum optomechanics or cavity optomechanics, where you couple an optical or microwave cavity to a mechanical resonator indicated by the spring here, and you have a radiative coupling between the two. The most famous example that I think all of you now know is LIGO, that has been used for the sensing of gravitational waves, but there exist many other realizations of force sensors or field sensors, and if you're interested in this field, there is a nice overview article. It's a few years back, but it's still, regarding the architectures, is still an interesting overview. Okay, so let's look at a protocol that produces a squeezed state, and this protocol is due to the Marquardt and Clerk groups, and they considered an optical cavity that is coupled to a mechanical resonator, and both of them are coupled to a reservoir by decay rates kappa and gamma. And what they saw is that if you're driving your optical cavity at the sidebands, which are defined by taking the difference with respect to the two frequencies, and you choose the amplitude of these drives appropriately, then you end up for the mechanical oscillator in a squeezed state. And because you're pumping into this squeezed state as a steady state, this is an example for what is called quantum reservoir engineering. And it's not just an interesting theory proposal. There also has been an experiment using not an optical cavity, but a microwave cavity, and they could show that indeed you can prepare the mechanical resonator in a state where it has less than one phonon in the mechanical mode. So it's really an interesting setup. And now the question is, can we speed up this procedure? So assume that we're starting in a product state. Then the original protocol consists in turning on the red and blue sidebands and wait. And that's slow. So instead now, if we assume the sideband drives to be time dependent, can we accelerate the steady state generation? That's a very natural control problem, and the amplitudes here have been called, and we keep this notation G minus and G plus. So here's the full model. Let me again skip over the details. We have decay via Lindblad operators, and the important quantity that quantifies the coupling between the cavity and the resonator and depends on our drive amplitude is called the cooperativity. Now, when we use our optimal control toolbox for this mixed state squeezing preparation, we see that we can speed up the approach to the steady state by up to a factor of 100, depending on how strong we drive. So what is shown here is the cooperativity that is needed to reach a fidelity of the steady state of at least less than 10 to the minus 4, and the time that is needed to achieve this. So the more you drive, the faster you can go. And interestingly, we find a power law relation between the cooperativity and the final time. And we did this optimization using both the Hilbert-Schmidt distance and this geometrically motivated new functional, and we find control solutions that are very similar in both cases. So what is shown in this panel, for example, the blue constant drive was the original protocol, and we find a soft modulation around it. That is what gives us the speed up. And we see that we reach the target state also in terms of the purity that we expect the steady state to reach. And just to illustrate once more the failure of the Hilbert-Schmidt product distance, you see that you're overshooting in purity and you're not reaching the kind of squeezing that you want. Now, let me highlight one point that is important for optimization theory, and that is we optimize here using the Hilbert-Schmidt distance and this split functional, but we had all these other distance measures that quantify how far we are from the target state. And we see that all of these other measures are minimized as well. That's not guaranteed, but it's a very nice feature that we can exploit later on. So let me just briefly summarize this example. You need to be careful to define your optimization target when you look at mixed target states. And in the case of optomechanics, we found that you can speed up easily within a factor of 200 within staying within experimental feasibility. Now let me come to the last example of this talk, and that is how we can use quantum control to improve state distinguishability in quantum sensing protocols. So the typical task in quantum sensing is that you have a system that undergoes evolution with an unknown field, and we characterize this here by two different fields, B1 and B2, that differ by a quantity delta B that we don't know. And they're subject to the same controls that can couple in all three directions. So we want to simultaneously control two qubit states, and we want their evolution to make the states as distinguishable at final time as possible, because that will give rise to the highest signal-to-noise ratio in quantum sensing. And we can do this using the Hilbert-Schmidt distance, as I showed you before. So that's what we're exploiting here. And we first look at such a sensing protocol, assuming that the qubits undergo T1 decay. And now, depending on the difference in your field that you want to be able to resolve on this delta B here, you need a certain minimum amount of time to make this states distinguishable, which is shown by this shape of the curves here. So we find that depending on the size of the field that we want to measure, there is a minimum time that we need to distinguish to resolve that field. That's nothing but the famous quantum speed limit. But what we also see is that if we optimize for longer and protocol duration, so longer than this minimum time, we can actually stabilize the distinguishability despite the T1 decay. And that was a bit of a surprise to us when we did this. And it's really a stabilization, so if we check the purity of the state, then it does stay constant beyond these minimum times here. How do the optimized fields look like? Well, we compare here the guess field, which is a Ramsey-like sequence, to our optimized field, and we see that, well, they are quite different, but still really simple control fields. And we also find that actually a single control field, just coupling to sigma y in that case, is sufficient. We can do the same, assuming pure dephasing, characterized by a decay time T2. And we see very similar features. So we have a minimum time, and we can stabilize the protocol, even though the pure dephasing is acting on our system. Also in this case, the shape of the field looks fairly simple, and again, a single control field is sufficient, this time coupling to sigma x. And what is important is that we can now exploit the fact that minimization of the Hilbert-Schmidt distance was equivalent to the Bürst distance that we found in this previous example on the squeezing. And now the burst distance in quantum sensing is directly related to the quantum Fisher information, which characterizes a metrological gain. So we can now plot this metrological gain as a function of the protocol duration, and we see that if we're using these optimized fields and we're willing to wait a bit longer, then we get a metrological gain, which is shown here in the difference between these dotted curves, which represent the Ramsey protocol, to the solid lines, which are our optimized curves given a minimum amount of field strength that we want to be able to resolve. How are we achieving this metrological gain? Well, for this, it's useful to look at the time evolution. I show here the time evolution with respect to the T1 decay, and in that case, we actually do have a decoherence-free subspace, which is the zero state down here. So what actually happens is that the control protocol is storing the states close to this decoherence-free subspace before bringing it back at the time when we want to measure and making them as distinguishable as possible. The strategy is very...
Roughly 30 minutes are over. Yeah.
I'm almost finished. Thank you very much. The strategy is very similar if you look at dephasing. It's just that the decoherence-free subspace now is a different one. So in both cases, T1 decay and T2 dephasing, the stabilization of the distinguishability is achieved by staying close to a decoherence-free subspace. So with this, I'm already at the summary of this last example. So when using optimal control theory for quantum sensing, we find two improvements with respect to the Ramsey protocol. And we were able to do this using the optimal control machinery, in this case, really our favorite tool, Kottov's method. And these two improvements consist in increasing the overall achievable state distinguishability at the expense of slightly longer protocol durations. And we can stabilize the state distinguishability at its maximum for times which are longer, at least an order of magnitude, than the decay time. And these two improvements can be realized with comparatively simple, intelligible, and experimentally feasible pulse shapes. And with this, I come to the summary of my overall talk. So I showed you three examples, one very briefly where we use optimal control to operate at the quantum speed limit and this way beat decoherence. And the example was the preparation of Rydberg states. Then I discussed an example of quantum reservoir engineering where we used optimal control to approach the steady state faster than before. We have another example in my group's work on trapped ions that I didn't discuss today, but that you can look up in case you're interested, where we also can identify which is the quantum reservoir protocol that we need to, in this case, generate entanglement. And finally, I showed you how we can use optimal control to protect against decay by operating close to a decoherence-free subspace, and that can be harnessed for improved sensitivity in quantum sensing. Now here's a picture of our group, and the Rydberg example was done by Sabrina in collaboration with the group at the Collège de France in Paris. The rest of the talk is really the graduate work of Daniel Basilevich, who just finished his PhD thesis. This picture was taken back when the group was still in Kassel. As you may know, we have recently moved to Berlin, and we're now busy trying to get the TV tower of Berlin into a non-classical quantum superposition. And with this, I thank you for your attention, and I look forward to your questions.
Thanks a lot, Christiane. Thanks a lot for showing us many examples of how to use quantum control for quantum sensing and optimal for open system quantum control. So I would have a question concerning the norms that you have and the minimization protocols, because you said the Hilbert-Schmidt norm is the one that you can use where the others are more complicated. Is there an easy way to see why this one is better than the others?
Yes. you see what the others have in common? They have this nasty square root.
Yeah, so and that causes then really numerical problems that you do not get the convergence.
Exactly. It's exactly. So it's the discontinuity, to be precise, that is hidden in this square root and that you cannot easily get rid of. But so it's really just a numerical problem.
But in principle, that doesn't matter because you say you get the same conclusions no matter which one you would take.
So in our optimization examples, we found that it really doesn't matter, but you have no rigorous mathematical guarantee for that because each of these distances measures something slightly different. But I think that the reason why in the end it does work is that what you're looking for in optimal control is not the exact size of the epsilon sphere around your target, which is different for these different measures, but what you're looking for is the right direction, and apparently this right direction is captured sufficiently well by the Hilbert-Schmidt distance.
Okay. Is there questions from the audience? Yeah, Federico, you were first.
Yeah, hello, Christiane. Thanks for the great talk. I just wanted to ask regarding the last example and the decoherence-free subspaces. So definitely I have some intuition for why the zero state is decoherence-free from relaxation effects. But I don't see how I think, is it the X, the plus state is free from the phasing. Is this just a numerical, so is this just a result of the way the Markovian noise is implemented in some master equation, or is it actually, would this also be true in experiment?
If you have an experiment that is subject to pure dephasing, then this would also be true, because then, I mean, of course, to be an exact decoherence-free subspace, that is determined by your Lindblad operators. Okay, but if we assume that this model for the decay is an appropriate one, then you should also be able to find this decoherence-free subspace in experiment. And I think what is really the interesting point here is because, of course, our model is with just a qubit evolution undergoing T1 decay or pure dephasing is really simple. But the main message is that in quantum sensing, it really makes sense to exploit decoherence-free subspaces. So if you know of a decoherence-free subspace, then go and use it. And we have another ongoing project that has been ongoing for some while, but we still hope that we can make progress there, and that is to use optimal control to actually identify these decoherence-free subspaces in more complex systems. But that's, of course, a whole task and a whole problem in its own.
Thanks so much.
Eugenio, sorry for not.
Yeah, I'm here. Okay. Hi, thanks, Christiane, for the talk. And I have two questions. The first one was actually regarding Stefan's remark. Maybe it's just I don't know if it makes sense, but why can't we take just like the square of these distances to avoid square roots? Does it make, because usually distances have always singularities in the origin. It's typical, but sometimes one takes a square root, the power of.
Sure, but even if you take the square root, even if you take the square, if you square the root, you would still have a discontinuity. So you don't have a smooth variation. That's the issue here.
Okay. And concerning the coherent free subspace. So it's interesting because we were thinking about something in contrast also with Mario and Lugot, was about taking a two-level system, but with a state with dispersion, with just one state of dispersion in some sense. So here you are taking one state, the span of one state will be unitary in some sense.
I'm not quite sure what you mean by dispersion, because so we do have separate time evolution drifts, right? So we have each of the states undergoes a slightly different evolution. So it's really the question of simultaneous control, and maybe the interesting angle here is that you don't know what is your target state. And you don't really care also. All that you care about is that the final state of these two qubits undergoing slightly different evolution is to make them as different as possible. So that's what we're doing here. But dispersion, I think, is already exactly what you have an ensemble of just two states in this case. And you want to make the time evolution of these two states as distinguishable as possible.
Okay.
But we can also discuss this together with Ugo and Mario at some point later.
Yes, of course.
So
thank you.
We had one more question, Aaron. We had two more questions, but I think I would like to postpone the other one for the breakout sessions. So Aaron.
Hi. Thank you for the very nice talk. So this, with regards to the squeezing research you presented, so you stressed that it requires to use the mixed state formalism. But what I'm a little bit confused about is that the squeezing states themselves, they are unitary. They are coherent states. They can be produced by a squeezing operator. So what I'm trying to understand is what part of the state space we are actually able to control in this case.
So in this specific model, maybe we have to go here to see this a little bit better. There is actually a trade-off, and I think that's what makes this an interesting control problem also, and that is a trade-off between purity and squeezing.
Mm-hmm.
So if you go to a fully pure state, then your squeezing vanishes. So that's not what you want. But this, it's really something specific to this that's modeled by Marquardt and Clark.
I see. Mm-hmm.
Okay.
Thank you.
Since we have a minute, so Jesper has the last question.
Hello, can you hear me?
Yes.
Yes.
Fantastic. Thank you for the overview of your latest work, Christiane. That was very interesting. I just had a quick question for your experimental collaboration. So you mentioned, of course, that when you do any kind of theory and you have to actually put it into an experiment, you have to have a good sort of theoretical model of what you're doing. And I was just wondering if you could briefly sort of highlight what kind of things you took into consideration. For example, you talked about you did things that were easy on both sides, so you sort of calibrated on a common ground. And I was just wondering if you could maybe explain a bit more how that process went and what you, that general process.
So we would have liked to take everything into account, but our experimental friends were not willing to fully determine the device response, because I think it's just, as you know very well, is super tedious and not very rewarding to do that. So the more practical strategy in this case turned out to be to make the controls as simple as possible. So. Okay. So you see that, for example, here in the beginning of our time evolution, the model and the measurements do not agree super well, but this may actually, or most likely after going back and forth a couple of times, we are pretty convinced that this is a problem of the measurement and not of the control. So we decided to live with it.
So
But
you get very smooth controls. Is that just due to regularization penalties?
no, so actually
Or not at all?
the crucial step in getting very smooth controls was to go to the rotating frame and optimize within the rotating frame. That already was sufficient.
Okay.
So we didn't even need further constraints.
Okay, so with this, let's thank Christiane and also Patrice from speakers for these sessions again. I clap hands. You can clap as well. And so we are all